Welcome to this video on quantum evolution, where we will derive and interpret the time-dependent Schrödinger equation, or TDSE. Our learning roadmap covers three key areas. First, establishing the physical constraints in the setup. Second, the mathematical steps to assemble the dynamical operators. And finally, interpreting what the symbols tell us about reality. We begin with Part 01, the foundations. Understanding why classical laws were insufficient for describing the quantum realm. Classical physics, based on Newton's F equals ma, calculates trajectories of point particles. However, subatomic entities behave as spread-out clouds of information, requiring a law for waves, not dots. In quantum mechanics, the state of a system is described by the wave function psi. It contains complete data, has a complex value with phase, and is probabilistic, where the magnitude squared is the probability density. Part 02 focuses on the building blocks, the fundamental relations that bridge energy and time, necessary for our derivation. The first building block, energy frequency, shows that total energy is directly linked to the oscillation speed of the wave in the complex plane, defined as E equals h bar omega. The second is momentum wave vector, illustrating that momentum is inversely proportional to the wavelength. Smaller ripples mean higher momentum, given by P equals h bar k. Now we move to Part 03, the derivation, where we perform the step-by-step mathematical assembly of the TDSE. Step 1, the trial wave. We begin with a complex plane wave, the simplest description of a free particle moving through space, which has a definite energy and momentum. Step 2, evolution in time. We differentiate the trial wave with respect to time, to see how the wave changes over time. Step 3, finding energy. We substitute our energy-frequency relation into the time derivative and multiply by IH bar, yielding the relationship for the total energy E. Step 4, spatial change. Next, we differentiate the trial wave with respect to position, x, to observe its change across space. Step 5, curvature and p squared. By differentiating again, we find the second derivative, representing the curvature of the wave. Step 6, linking to momentum. Substituting the momentum wave vector relation, k equals p over h bar, and rearranging, we isolate the term for the classical kinetic energy. The foundation for combining these parts is the classical law of energy conservation, where total energy equals kinetic energy plus potential energy. Step 7, the master assembly. We map our classical energy terms to their quantum wave derivatives to assemble the complete time-dependent Schrödinger equation. This final result is the complete TDSE, the governing law of the quantum universe, describing how the wave function evolves in time. Part 04 is dedicated to the interpretation, going beyond the symbols to understand what is actually happening in the quantum world. The imaginary unit I is vital. It ensures the wave function is a rotating vector in the complex plane and allows for interference while conserving total probability. Unitarity is key. The TDSE ensures that if a system starts with a total probability of 100%, it remains 100% forever. Probability is conserved. The term in the brackets of the TDSE is called the Hamiltonian operator. H hat acts as the generator of time evolution for the system's wave function. The TDSE provides quantum determinism. If you know the initial state, the equation calculates the future state perfectly. Determinism is only lost during measurement. Part 05 explores time independence, the special case where time stops influencing the dynamics. If the potential V is constant over time, we can separate the solution into spatial and temporal parts, simplifying the problem considerably. Plugging this split wave back into the TDSE gives us the temporal solution. This result is just a rotating phase that does not change the probability density. These solutions are called stationary states, where the physical outcome is frozen in time. These are the energy eigenstates that solve the time-independent Schrödinger equation, or TISE. Real motion occurs when we sum different stationary states. The beating frequencies of their phases create movement in the overall quantum system. Let's summarize the revolution we've covered. The derivation recap. Start with the free plane wave. Use time and space derivatives to find the energy and kinetic operators and merge them using energy conservation. The physics recap. Energy drives the time phase rotation. The imaginary quote I ensures probability conservation, and the spatial curvature of the wave is the kinetic energy. Finally, let's look at the advanced frontiers, where the TDSE takes us next. The TDSE is used to model phenomena beyond stationary states, such as quantum tunneling and decoherence, where information leaks and turns quantum systems into classical ones. As Richard Feynman said, if you think you understand quantum mechanics, you don't understand quantum mechanics. This field is constantly expanding. Thank you for watching this deep dive into quantum dynamics. Feel free to explore more advanced topics.